Good morning or good evening, depending on where you are. Thanks for joining the Women in Power track session at Powering the Future Summit 2021, hosted by IEEE Power and Energy Society Young Professionals. Myself, Preeti Warrior, working as a wind and solar siting engineer at Vestas and serving as the Women in Power liaison, IEEE Power and Energy Society Young Professionals. I'm really excited to introduce the track and our eminent speakers. Dedicated to the theme, Role of Women in Recent Renewable Energy Technologies, this track is focused on introducing four trending areas under discussion in the renewable industry, which are digitalization, energy storage, electric vehicles, and green hydrogen. And it also covers the various opportunities for women in renewable sector. Unfortunately, one of the speakers couldn't join us today due to urgent family commitments, but we have four excellent speakers who will be taking us through the technical ride with their experiences and immense knowledge in the subject. Before starting, I request all the participants to make use of the chat window to post your queries and comments. I hope you will have a wonderful learning experience. Digital technologies have started gaining more attention in renewable sector these days. With high volume of data come more opportunities on utilizing the data to improve the asset performance, reduce component failure rates, and for accurate forecasting of generation. Digitalization plays an important role at each stage of the project. To share more on what is digitalization, where can digitalization be applied in renewable assets, I welcome Lucy Craig, Senior Vice President and Director of Growth, Innovation and Digitalization at DNV. Lucy is responsible for scaling new ventures, digitalization, innovation, and technical governance across service areas covering the energy systems value chain from generation and production, transport, transmission and distribution to energy use. She directs energy systems strategy for innovation and growth in new technologies and processes, including top growth priorities such as hydrogen, digital assurance, solar, and offshore wind. A top priority for Lucy is supporting DNV's customers in accelerating the energy transition. Through advisory, monitoring, verification, and certification services, DNV provides assurance to the entire energy value chain across generation and production, transmission and distribution, and end use. DNV supports the operation of high risk assets and systems, both physical and digital, in wind, solar PV, energy storage, hydrogen, oil and gas, synthetic fuels, power grids, and carbon capture and storage. Prior to her current role, Lucy managed the region of Iberia and Latin America for DNV in renewables advisory. Lucy has 30 years' experience in the renewable industry. She has a PhD in electrical power engineering and is a fellow of the UK Institute of Engineering and Technology. It's with pleasure that she has always accepted my invitation, and I'm so happy that you're with us here today. A warm welcome to the summit, Lucy. Over to you.
Preeti, for that introduction and for the opportunity to present this afternoon. I will share my presentation and make sure that you can see it. So I hope you can see my presentation now. As Preeti mentioned, I am Director of Growth, Innovation and Digitalization at DNV. And what I want to talk about today is, first of all, the rapid changes that we're going to see in the energy sector. And with that transition, the role of digitalization, the opportunities that it provides, and some particular case studies where we see that optimization of wind and solar and also hybrid plants is only made possible through the application of digital technologies. I'm going to start by giving a broader view of the energy sector. We in DNV each year carry out our own analysis of the expected energy mix in the decades out to 2050. It's a detailed analysis of energy supply and demand based on the most economic choice for energy generation and energy transport over the coming decades. What we see, of course, is that will be a very rapid transformation driven by the rapid reduction in costs of variable wind and solar, and also to some extent by policy. What we see this year in our 5th analysis in the report that we launched just last month is that the COVID-19 recovery spending, unfortunately, has been a lost opportunity. We could see in our analysis last year that there was a rapid drop in emissions, but of course for all the wrong reasons, because there was also a rapid drop in economic activity. But what could have been an opportunity for a green recovery has not in general been adopted, with the European Union being an important exception, and to some extent the United States, but largely, including in North America, around the globe, governments have sought to bolster the existing industrial situation and rather than looking for green alternatives. So we are very far from achieving the Paris Agreement ambitions. Despite that, there are going to be very rapid changes. We expect to see electrification doubling its share of the final energy mix. And even though variable wind and solar provide new challenges to power system operation, they are not roadblocks to a rapid growth. We see that fossil fuels will still play an important role out to 2050, with final energy demand being covered roughly 50% by renewables and 50% by fossil fuels. And what we see is that the much needed decarbonisation of gas and deployment of carbon capture and storage will be too slow to really make an impact in the hard to abate sectors. And so the broad messages of our energy transition outlook this year is that much more hydrogen is needed, more biomass and fuels are needed to, and also more hydrogen generated from dedicated renewables to really have an impact and be able to meet the goals of the Paris Agreement. Despite the fact that we're not moving as fast as we need to meet the goals of Paris, we do, of course, see a very rapid transition. And by 2050, we expect that 70% of electricity will come from solar PV and from wind generation. That brings new challenges for power system operation. And we see, of course, that there will be new power lines installed at HVDC. There will be hybrid grids combining HVDC and AC. And so system operation will become much more complex. Also, we see that in many countries, the requirement to operate assets for extended life and closer to their thermal limits, either due to limitations in being able to build new infrastructure, which is in the case in some countries in Europe, or because the increasing demand for electricity means that infrastructure will be operating closer to its thermal limits. And there will also be more dynamic interactions with end use. At the other end of the scale, from the large supergrids that we will see operating at extra high voltage, connecting countries and nations, for example, in Greater China and in the Indian subcontinent and also in Europe, the rise of the supergrid will be balanced at the other end of the scale by a much more complex distribution network, where we see the growth of distributed energy resources, also much more active demand response, and the need for greater flexibility in load. All of those will require close to real-time interactions, and that is only possible through automation and increased digitalization. So we see that digital technologies, the use of greater connectivity, the better access to data is an important enabler, both of decarbonization and also decentralization. If we look to see some more particular examples of how digital technologies are used in the energy sector, we see, of course, use of blockchain for decentralized energy transactions, for peer-to-peer trading. We see the wide adoption of artificial intelligence and machine learning in enhanced forecasting models, for example, for forecasting power prices, but also forecasting power output from wind and solar plants, and also giving new insights into operational asset data sets. We see the rise of platform businesses to allow data sharing between asset owners and asset operators, the extended use of drones and remote sensing, for example, for drones for inspecting wind turbine blades, but also for inspecting solar plants. And then many other applications. I'm going to show some more applications of digital twins, but also the way in which sophisticated algorithms and modeling techniques are being used to make the wind and solar industry more efficient. But before I dive into that, digitalization has become rather a hype. And so we wanted to look into what really digitalization means for players in the power and renewables industry. So we carried out a survey of around 2,000 stakeholders, customers of DNV, key players in the power and renewables sector. We also, on top of that, carried out in-depth interviews with these 5 key industry players in the renewable sector: Macquarie, an important investor; Goldwind, the OEM; LO3 Energy, which is a platform for distributed energy based in Australia; PSE&G, a utility in Northeast USA; and RES, one of the largest owners and operators of renewable power plant. We asked them why they considered digitalization, how they were applying that, and we got a lot of important data and statistics. I don't have time today to go into all that data. I'm just going to share some of the highlights. We saw that while the vast majority have a digital strategy, only a small percentage, only about 20%, considered themselves digital leaders. The main role for digitalization was reducing costs and improving efficiency, and perhaps that's not surprising in a sector where there is continued downward pressure on costs. And the way in which digital technologies can help to improve efficiency obviously helps in that downward trend. But I think one of the most important outcomes from our survey was to highlight that digitalization is not only about technology, it's also about changing the way that we work. And often that is the most challenging aspect, that the uptake of digital technology is often really only possible at a broad scale if individuals are willing to look at new ways of working, changing the way that they see work processes. And also an important outcome is that digital technology on their own really can only be powerful when combined with deep domain knowledge. And so really to make the biggest impact, it's that combination of understanding digital technologies and their possibilities combined with the engineering technology that can really have an important impact in how systems operate. If we look now more specifically at wind, of course, in the wind sector, digital technologies have been operating for a long time, for example, in forecasting output, in optimizing the operation of assets, in reducing operation and maintenance costs. And we see an increased focus on getting value from data, particularly during the operations phase. We see that domain expertise and data expertise are in high demand, but also there's some challenges around data sharing in that many players are often reluctant to share data due to confidentiality issues. When we move to the solar sector, we see that solar, being a newer technology, was definitely digital native, is more advanced in the uptake of digital technology. And blockchain is one of the examples that was used. We see that the players in the field tend to have higher digital skills, and also huge opportunities and also uptake, as mentioned, the use of drone and aerial imaging to help reduce costs, and the great opportunity for using data analytics to improve operation. I'm going to dive into 3 case studies now. The first one is looking at how wind farm operation can be optimized. The traditional way to improve operation of a wind turbine is to look at the wind turbine individually. And we look to maximize revenue, reduce operational costs, and also maximize the return on investment over the lifetime. In practice, we see that, of course, these play off against one another. If we want to maximize revenue generation, we will also normally have a detrimental impact on operating costs. And so if we want to carry out an optimization of these 3 parameters, we need to take a whole wind farm approach. And wind farm control is a way of looking at how a wind farm can be managed. And the next slide shows some of the technical details with an example of Horns Rev, with the first offshore wind farm that was built, where we look at altering the direction in which the wind turbines in the front row of the wind farm are facing to reduce the loads on the wind turbines that are in subsequent rows. Of course, by turning their direction slightly out of the wind, then we also reduce the energy production, but there's an optimization process to ensure that we get the maximize energy production while also having the most beneficial loading on the wind turbines throughout the wind farms. And so using modern simulation techniques and using real-time data acquisition and advanced control algorithms, it is possible to both increase energy capture, but also achieve reduction in loading. And DNV is currently working with a number of players across the energy sector to look at the bankability, so how financeable it is to achieve these improvements in performance and ensure that lenders have the right information to have the confidence that the wind farm has the added value that this approach can bring. My next example is to look at the role of digital twins in wind turbines. And so wind turbines, of course, have huge data sets which can be accessed through the SCADA system. And they give, and it can be done through real-time data or data gained at high frequency and analyzed post-processing. And various opportunities can be explored in terms of analyzing availability, looking at shifts in power curve performance, detecting suboptimal control modes. What I want to talk about here is wind turbine life estimator. So with an aeroelastic model of the wind turbine, it is possible to look at the particular site conditions at the locations in which these wind turbines are installed. And based on their operating life and based on the detailed analysis, be able to predict the remaining life of the wind turbines. I have an example of where we have carried out this analysis for a portfolio of wind farms in the UK. Greencoat UK Wind is the largest non-utility owner of wind farms in the UK. And we carried out an analysis of their major structural components across their portfolio, looking at those which were non-replaceable, such as the tower, the foundation, the blades, the nacelle. And through our analysis, we could see that although the initial design calculations had been based on a 20-year life, given the particular site conditions, these wind turbines had a useful life of 30 years. That had a huge impact for Greencoat UK. We delivered our report to them one Thursday evening after markets had closed. And on the Friday morning, when markets opened again for trading, their portfolio had an overall 4% increase in value, representing an increase in value of around £62 million through the simple application, well, not so simple application, but through the application of digital technologies to be able to have a better understanding of the lifetime of their assets. The final case study I'm going to share is looking at the role of energy storage and renewables, so hybrid plants. We can, of course, see that energy storage and currently lithium-ion batteries are the favoured choice for energy storage, will play an increasingly important role as an enabler for the integration of the large amount of variable renewables we expect to have on the network over the coming decades. One market where we see particularly a large amount of battery storage being installed is in North America. And so the example I'm going to share is from North America. When we have battery storage and PV plants installed together, that opens up a whole lot of new possibilities in terms of the configuration of the power plant. And I've shown here the way in which the plants can be installed through the traditional AC coupling by the connection to the network, but also we can reduce some of the transformer infrastructure by having DC coupling. Now, there are a number of other questions that are raised when we come to installing a hybrid plant. We want to be able to understand what will be the revenue generated over the life. And for that, we need to understand what future power prices are likely to be. We need to understand the expected resource at the site, but also we need to have a detailed modelling of the battery life, its degradation curve, and the requirements for charging and discharging to maximise battery life. So there are a huge number of variables to take into account, and it's a complex optimization challenge to really be able to understand what will be the return on investment for such a plant, and therefore be able to understand whether the investment will be feasible or not. We are carrying out this analysis for a number of projects around the globe, but in particular in North America, we have a customer that had taken over 16 legacy gas peaker assets across 3 US states and was looking at the viability to upgrade these to storage or to solar plus storage. And as shown on the previous slide, that is quite a complex optimization and technology challenge to really understand what future revenues will be, and therefore to understand what the likely return on investment will be. And through applying optimization algorithms, through looking at all the different variables and how they will vary over the life of the plant, it's possible to be able to provide assurance to an investor on the likely return and the likely outcome and performance of a hybrid plant such as this. So these are just 3 examples of how digital technologies, how data is used to improve performance, to enable the transition from conventional plant to more complex power, renewables and storage plants. And of course, there are many other examples, but I would be happy to hear your questions on those.
Thank you so much, Lucy. That was a really insightful session on the various applications of digitalization, specifically on the case studies that you've provided. We have one question from one of our participants. So in the hybrid power plants, how the tariff structure is made for the energy storage system? I'm not quite sure if this directly applies to your session.
Yeah, the particular case I was showing is made complex because actually the plant bids into the merchant, the power market. So there's not a fixed tariff. It's the power plant gets the market price when it's generating. And so therefore that is part of the complexity, to understand how the power market prices will evolve over the coming hours in the operational phase or over the lifetime of the plant in the design phase. And therefore make the choices of when electricity is going to be used to charge the batteries, or when indeed the batteries will be discharging because there are high prices available. So that particular example I showed, it's not a tariff structure, it's the variable market price. We do, of course, have other applications where we look at solar and storage in standalone, or where there are PPAs with fixed prices. And of course, that will vary from one example to another.
Thank you for that. You explained a lot about these applications of digital technology. So there might be some confusions or dilemma among the young professionals or freshers on how to avail those opportunities. What are the different opportunities that are there? Is it same for the freshers or young professionals, or is it different? And what kind of preparations do they need to undertake?
Well, I think it's a huge opportunity now, of course, to enter this rapidly growing and changing renewable energy sector. And I would say that, of course, digital technologies are going to be important. So grab all the opportunities you can to learn about coding in Python, for example. Most of our young engineers have Python coding capability, and that's where quite a lot of our tools are being developed. And I see it's a continuous process. Each year, if not each month, we have new ideas coming up about ways in which we can automate processes. And so more and more we are seeing the use of programming, but also I think looking at how at the broader scale, understanding how large data sets can be fed into machine learning algorithms to then automate decision making, which in the past has required more manual intervention. So there are so many applications, but I think grasp all the opportunities you can, whether it's programming, whether it's machine learning. But I think never to forget that actually where that really is powerful is where there's deep domain knowledge. So I think also, it's particularly as an electrical engineer myself, I think it's very, very important to really have a good understanding of the fundamentals of how power systems operate. That is going to be so important in the future. And it's that combination of digital and data that is digital and domain that is really powerful.
Yep, I also completely agree to what you said. And even at different stages of your career, it's important to keep learning what is new and what is coming in the industry. So, with this incorporation of digital technologies, what is your opinion on the cybersecurity risks? Which mitigation measures can you advise?
Yes, and of course, cybersecurity is an ever-present risk, and in fact, ever increasing. And it's an area where my company and companies around the globe are dedicating increasingly higher resources. What we always say, of course, is that it is the weakest link, which is often the attack vector. And therefore, companies such as my own put a lot of emphasis on training, learning, making sure that everyone is aware. And I think that's what we should all be aware of, that clicking on links is something you should never do unless you know where it's coming from. And there are very, very simple actions that we can all do to really make sure that our systems are secure. But yes, particularly in the critical infrastructure where we are working in the power industry, cybersecurity remains a very important risk in an area where a lot of attention is paid.
So I hope participant you got the answer for that. So when you try to incorporate digitalization in the already existing renewable assets, do you see any kind of challenges from the customer side, whether it is convincing them or making them understand the importance of these technologies? So how do you tackle all those?
Yes, I think I'd like to go back to the questionnaire or the survey that we carried out. And what I see is digital technology, of course, is really important in that as a key enabler. But actually, one of the biggest challenges is the uptake, whether it's with customers, whether it's with asking people to change the way that they have always operated. And I think any of us who've been asked to use a piece of software for the first time, usually it takes a few tries before we're comfortable in using it. And that's often the same with any new tool that can bring a lot of benefits and efficiency. Often there's a challenge in learning how it operates. And that goes the same way with any time we ask people to change the way they are working. And so that goes back to the point that really, a key factor in digitalization is not just digital technology, but having the willingness for people to change the way that they work, to try something new, to look and see how we can be doing things better than the way that we do them now. And so having that mindset, that forward-looking growth mindset is a really important part of digitalization as well.
Thank you so much, Lucy, for that. So I think we are running a bit short of time. We do have a lot more questions. So if the participants don't mind reaching out to you directly if at all you have any queries.
I'd be happy to speak with any of the participants. That would be great.
Sure. Thank you so much, Lucy. So as a token of our gratitude from the IEEE Power and Energy Society young professionals, I would take this opportunity to thank Lucy for accepting our invitation and giving a very insightful session on digitalization in power and energy sector. As she rightly pointed out, there are a number of opportunities, not just for the experienced guys, but as freshers or young professionals. If you're really interested in working for the renewable sector, you have ample opportunities which you can make use of it. And once again, thank you, Lucy. Thank you for being part of this summit.
It's been a pleasure. Thank you for inviting me, Preeti. Pleasure to take part. And I wish you a great session the rest of the day.
Thank you so much. With greater penetration of renewable come greater challenges, especially with hybrid energy systems getting more focus. It is important to find best solutions to store the excess energy produced from the renewable sources and for their proper utilization. We have with us today Dr. Rahul Valawalkar, President and MD of Customized Energy Solutions India Private Limited, to share us the opportunities for R&D and manufacturing of advanced energy storage technologies in India. Rahul leads the emerging technologies domain for customized energy solutions globally. A strong votary of improving energy storage and e mobility in India, Rahul founded the India Energy Storage Alliance in 2012 and continues to serve as its president. He served as board member for Energy Storage Association USA during 2009 to 15 and as the chair for Global Energy Storage Alliance during 2018-2020. In 2021, Central Electricity Regulatory Commission of India inducted Rahul to be part of the Central Advisory Committee of the Power Regulator. He played an instrumental role in shaping up the Advanced Chemistry Cell Battery Manufacturing Program for Niti Aayog during 2019-2020, under which 50 gigawatt hour of manufacturing capacity is expected under the Production Linked Incentive Scheme for Government of India. During 2018-19, he worked on drafting the National Energy Storage Mission for MNRE. In 2020, Rahul received the Global Young Entrepreneur Excellence Award for his valuable contribution and leadership in the field of energy storage and renewable energy at the World Renewable Energy Technology Congress. In 2018, he was also recognized with India Smart Grid Forum President's Award for outstanding contribution to growth of smart grids in India. He is the recipient of Energy Storage Crusader Award in 2017, Institution of Engineers India Energy Award in 2014, and Computer Society of India's Young IT Professional Award for 2000 and 2001. Rahul holds a PhD in Engineering and Public Policy from Carnegie Mellon University, Master's degree in Energy Management from NYIT United States, and BE from Walton College of Engineering, India. It's my pleasure to welcome Rahul to this session. Rahul, the stage is yours.
Very much, Preeti. It's a pleasure to be here for participating in this program. And let me try to share my screen. I hope you can see the presentation now. So, okay, I'll go ahead. So, thank you, Preeti, once again for inviting me for speaking on this prestigious platform. So, for people who are not familiar with customized energy solutions, CS is a global company headquartered in Philadelphia, and I lead our India operation, which is headquartered in Pune. CES is a consulting and services company where one of our differentiator is we currently manage more than 13 gigawatt of assets on behalf of more than 500 clients around the globe. We also have experience in managing close to gigawatt hour of energy storage assets and actually optimizing and dispatching those in electricity market. And as part of such fleets, we are also managing certain electric vehicle fleets and operating those in markets. Our emerging technology team works on looking for breakthrough technologies which can disrupt the status quo in both electric grid as well as transportation sector. And for last 15 years, we have worked with more than 200 companies and helping them in technology commercialization. In India, in 2012, we also started India Energy Storage Alliance for creating awareness about advanced energy storage technologies in India. And in 2016, we upgraded our mission to make India a global hub for R&D, manufacturing, and adoption of advanced energy storage and e-mobility technologies. I'm happy to inform that over last 9 years, IESA has now grown as a strong industry alliance where we have now close to 150 members across the complete value chain of energy storage, e-mobility, green hydrogen ecosystem. And we have additional 30 plus partners with whom we work very closely for accelerating these efforts. Now coming to batteries, again, although in terms of the grid side applications, the discussion has been relatively recent, but when it comes to the e-mobility, quest for new batteries is not new. The screenshot what you're seeing is a cover page of Scientific American magazine from 1911. featuring Thomas Edison. And if you see the right hand side image, basically it says 1,000-mile endurance run. So it was not 1,000 mile on a single charge, but basically that time, with the limitation of the lead acid batteries, Thomas Edison was working on nickel ion batteries, and the goal was to have the batteries last for a total driven distance of 1,000 miles. Now, in recent years, you may have heard about the million-mile battery from Tesla and Professor Jeff Dan, what is getting commercialized right now. So now, in fact, we are looking at most of likely vehicles are not going to last for a million miles. So what you do with the batteries and how you use them for stationary applications after they serve its basic purpose for the e-mobility area. Now, when we look at energy storage, it is not only about batteries, and within batteries also there are almost half a dozen different type of chemistries. Apart from lead acid, lithium ion, there are flow batteries, there are metal layer batteries, there are range of new electrochemistries which are getting commercialized right now. But energy storage is not limited to only batteries. There are other mechanical technologies like flywheels, compressor energy storage, gravity based technologies like pumped hydro, or people are now looking at moving different weights around and try to use the same principle of pumped hydro for decentralizing gravitational storage. There are thermal storage technologies which can be used for both storing heat as well as cold. There are chemical storage technologies such as hydrogen, which can be used for fuel cells and electrolyzers. And you can create again a reversible solution where you can use excess electricity for generating hydrogen with electrolyzers and then reuse that hydrogen either for direct industrial commercial applications or use it in a fuel cell for regenerating electricity. And there are other electrical forms of storage technologies like ultra capacitors, which can be used for hybrid applications or for any pulse applications. And obviously most of these storage technologies require power electronics for conversion, so that is also becoming integral part of the ecosystem. Now, why you are hearing a lot more about some of these advanced battery technologies is that in last decade, the cost of these batteries, particularly lithium-ion batteries, have come down very rapidly. The batteries for some of the initial grid scale projects when I was involved back in 2008-2010 timeline were more than $1,200 per kilowatt hour, and now at a cell level this price has come down in 2020 to almost around $100. At a system level you are still looking at $200-$250 per kilowatt hour as a price, but you can see the 10x price reduction which has happened because of scaling up of manufacturing as well as improvement in the technology, particularly the increase in the energy density, where now you can use less materials for producing same energy. So in this regard, as a India Energy Storage Alliance, we have launched more than 15 initiatives to try to address some of the knowledge gaps in India and try to also encourage a lot of international collaboration in this area. The energy storage and EV policy is quite rapidly evolving, although it may seem a long journey with 8 years, but having played a role in influencing policies in US, I can say that even actually India to some extent has moved ahead with many of these policies in a little bit faster timeline. Although obviously as a industry stakeholder, you always wish for a little bit faster action. But particularly in last 3 years, I would say that the things are moving very, very rapidly. In fact, the awareness and importance of energy storage and e-mobility is acknowledged right at the highest level by Prime Minister himself. And Niti Aayog, which is a central policy think tank for central government, has been working on creating policies for transformative mobility as well as battery manufacturing. And they have been involving various industry stakeholders, and IESA has been one of the stakeholders which has provided inputs for many of these policies. And these policies have now resulted in creation of National Hydrogen Mission, as well as there is a RFP announced earlier last week, where India is looking at generating 50 gigawatt hour of battery manufacturing on an annual basis within next 3 to 5 years. Now, why do we need storage? Obviously, on the e-mobility side, it is obvious. But again, now as we are moving towards renewables and with the fall of renewable energy, solar and wind has become the cheapest energy source for the grid. And if you see US or India, solar and wind are becoming as a together as a renewable energy one of the fastest growing energy resource. And people think that if you add wind and solar and create a hybrid, then you may not need any form of storage. But if you see most of the regions, then wind and solar, even if you add, it does not match the load shape. Typically, the late afternoon, early evening period is the period where you do not have definitely solar energy, but also wind energy typically picks up later in the night. And that's a time where you need additional balancing resources. Also, there are early in the morning or in the afternoon, with the kind of solar penetration we are looking at, you may actually have much excess generation which is happening during the day. So if you can store that and use it in the evening, then that actually makes us operate in a much more cleaner and greener grid. Now, people question, does the economic allow this? Isn't it very costly to install additional storage technologies? Lucy mentioned about it is very complex to do this type of economic analysis, because there are many parameters which you need to consider when you're looking at levelized cost of storage. You need to not only consider about the capital cost and cycle life, but you need to consider round trip efficiency. You need to decide for which application you are using storage, what type of a charging discharging rate the storage will be used, because that will have impact on actually cycle life. What type of a depth of discharge in each cycle you will utilize it, because that also has an impact on cycle life. What type of a renewable tariff and what profile of renewable energy is available, because that will determine the sizing of the storage. So you need to consider all these parameters to come up with a levelized tariff. So here we have represented just couple of simple examples in terms of 1 hour and 4 hour storage with 50% in terms of the power rating. And you can see in terms of the marginal cost, storage may seem very costly, where right now in 2021 you are looking at, depending on 1 hour or 4 hour, as a marginal cost you are looking at 6 to 11 rupees. But if you see the blended tariff, then actually it is much cheaper, where now you can have for 4 hour systems you can have a blended tariff of RE plus storage of around 5 rupees or even less than that. And if you are storing only 1 hour of energy and use it mainly for balancing and improving your scheduling, then you can even get RE plus storage for 4 rupees. And in next 5-6 years, it is expected to have another rupee or rupee and a half drop in this tariff. So if you even see a commercial industrial customer who is right now buying power from grid, especially in the Indian context where CNI customers pay the highest tariff, the hybrid plus storage prices are already becoming cheaper than purchasing from the grid. Now, because of these complexities and because of variations in the technology, variation in the load profile, variation in renewable generation, you need to look at a lot of iteration to make the proper decision. So we have actually, as a CES, developed a platform called Comets, Comprehensive Market Evaluation Tools for Storage, which has been used for more than 200 projects around the globe for doing financial due diligence, and many of these projects have gone ahead. And as I mentioned earlier in my opening remarks, we are actually operating these assets. So it's a very evolving field. We are continuously actually developing these algorithms. Some of the initial work on this was started when I was doing my PhD at Carnegie Mellon University, but over last 10 years, using the actual operating experience, we have added a lot of features in this analysis, as well as the market rules itself keep on evolving. So you cannot just make certain assumptions. You need to have this type of analysis very customized based on each location where you are looking for installing such RE plus storage projects, and you need to understand the market regulations, the other dynamics, as well as the customer specific parameters. Now, one question which many people ask is that, oh, especially in the Indian context or even in US or other places where there is a sufficient thermal generation which is already installed and it is not being operated, why don't we just rely on thermal generation for balancing the renewables? It is a very valid question. The challenge is, why are we going and adding all these renewables? Because if we just wanted to rely on existing thermal plants, then we could actually scale down significant amount of renewable addition what we are doing anyway. But we are adding renewables because we have certain environmental goals. We want to achieve certain carbon neutrality, improve the air quality, reduce the pollution. And while doing that, if we start relying on existing thermal plants, or even in fact worst case would be building new thermal plants just as a balancing units, then you lose significant part of both CO2 emission reduction, because at partial load thermal plants have higher heat rate. That means for generating same energy they will be consuming more fuel, and in return emitting more CO2 and other emissions. And particularly at partial load, the SOx and NOx emissions, which are very important for the local air quality, those take a significant hit, and you may lose as much as 100% emission reduction unless you have a very strong emission control equipment. And especially in the Indian context, that doesn't exist. So it is very critical that we do not fall into this trap, that just try to say, okay, because there is some existing assets, we try to just use them for balancing. Because ultimately, if you are using the base load thermal plants as a peaker plant, considering your fixed cost plus your variable cost, what you are paying them, then actually you are already paying more than 8 rupees. And RE plus storage units, new installation, are now cheaper than that. Now, this type of RE plus storage also has an application in terms of microgrids, and this is the area where I think these microgrids can be both in terms of rural as well as for campus microgrids. So since 2016, IESA has been working on a project called Microgrid Initiative for Campus and Rural Opportunities, where we have looked at various aspects such as understanding why some of the existing microgrids are failing. Is it a technical issue? Is it an operation maintenance issue, design issue? And based on that, we have created a detailed manual under a support from USAID PES fund. And we are also in fact working on right now a project with European Space Agency, where we are looking at role of satellite data for improving microgrid design and microgrid planning, as well as providing series of value-added services beyond just providing access to basic electricity. And we are very much committed to looking at these microgrids more from the economic development, and looking for especially how you can use these microgrids for developing agro businesses, which can empower women in some of the remotest locations in India or in Africa. Globally, over last 5-6 years, the energy storage deployments are increasing very, very rapidly. This is a snapshot of projects which are monitored by US Department of Energy. Again, just one disclaimer is this is not a complete data. This is just a data which is being monitored by US Department of Energy. So some of the regions like China or India, where they do not get full data, all projects are not listed. But you can just see at a high level some of the hotspots which are emerging, right? California, northeast of US, Europe, Korea, Japan. So these are some of the regions where I think there is a lot of policy support and activities which is happening. But I'm pretty confident that in coming decade, you're going to see such hotspots emerging around the globe. In India also, we are tracking such projects, and even not just projects, but the manufacturing facilities, R&D facilities, the charging infrastructure facilities. If you're interested in knowing about that, you can visit the IESA website and look for India Energy Storage Database. And over last 3 years, there are small scale projects which have been done, starting with around 500 kilowatt projects done by Power Grid, then around 16 megawatt project deployed in Andaman Nicobar by L&T, as well as AES has deployed a 10 megawatt hour project in Delhi for providing grid supports. And now, in fact, Indian government has recently come up with tenders which are for gigawatt hour scale deployment of storage. So in next 12 to 18 months, you are going to see this scenario completely changing, and we will see a lot more projects coming up all over India. Now, in terms of the e-mobility, it is very important that although now electric cars are becoming more popular, companies like Tesla have shown that there is a very strong consumer demand. But in India, particularly, there is a tendency that many customers are waiting for sort of a perfect car or a cheaper car 2 years, 3 years, 5 years down the line. And many times we get corporates who commit to achieving some percentage of penetration in 2030. But what we as IESA believe is that there is a need for accelerating this and look for doing first 10% of electrification within next year or maybe 18 months at max. So we have developed this tool under EV adopter circle, where we can monitor the fleets of existing corporates or even individual users and help them understand if they can switch to e-mobility in an economical way. And then our goal is to try to encourage corporates to at least find out 10% of their fleet vehicles and switch them to electric within next 12 to 18 months, and then take it to 50% over next 5-6 years. One of the things which can help in this area is some of the innovative options, such as not just focusing on the charging infrastructure, which anyway we are doing, but also looking for alternate business models such as battery swapping. And as IESA, we have been doing various roundtables to understand what are the barriers for kickstarting this ecosystem around battery swapping, because we have some of the members like Exicom, Sun Mobility, Okaya, who have already introduced these solutions in India, but we need to do a lot more to remove some of the barriers so that each company individually doesn't have to spend a lot of resources in fighting out these issues, and we can actually create a launch pad so that we can accelerate this adoption much faster. We also have recently seen Gogoro, which is a global leader in this area, has partnered with Hero and has announced they will be also introducing these solutions in India. So overall, as a IESA, we project that the stationary plus EV market as a base case scenario between 2020 to 27 is worth almost around 400 gigawatt hour, and in a best case scenario, it could be over 700 gigawatt hour. And again, right now, the way the policy push is happening from the government as well as interest from the industry and consumers, we are pretty confident that we will end up in a scenario somewhere between base to best case, possibly closer to the best case scenario. Now, with this, considering this upcoming demand, as I mentioned, since 2016, IESA has been working on pushing for policies for supporting manufacturing. So earlier this year, the Indian government has announced a battery manufacturing production link incentive program, where the tender was just announced earlier last week, where 50 gigawatt hour of tenders are invited by Indian government with minimum 5 gigawatt hour facility and up to 20 gigawatt hour facility to be constructed by one single company. So depending on the response, minimum 3 gigafactories will be set up in India, but possibly even 6 to 7 gigafactories may get set up if everyone doesn't go for a 20 gigawatt hour factory. Apart from this, there will be additional 5 gigawatt hour tender for niche SEC program, which will come in, where some of the next generation technologies which are right now in early stage of commercialization can also be used. So as the IESA, we don't want to be happy just with a 50 gigawatt hour target, because we think the pace at which global competition is hitting up and as well as the demand in India is picking up, we cannot just wait for 50 gigawatt hour. So we have already set up a target where we want to get to 100 gigawatt hour by 2030 and continue to build on to 500 gigawatt hour by 2035 as a manufacturing capacity. And there also we are targeting that by somewhere between 2030 to 35, we should be aiming for this production to be completely green production, so that some of the people who ask questions about are these batteries really sustainable, their questions can be answered. Simultaneously, we are also launching an effort on looking at greening up of the complete supply chain and identifying the sustainable practices for the supply chain, looking for recycling practices. So all those efforts also will be taken up in parallel while we are setting up these gigafactories. Now, this is the area where there are a lot of international collaboration opportunities, because although many countries are looking for localizing these aspects, I don't think in terms of the raw material, you need to be focusing just on local raw materials, because there are enough raw materials available around the globe and different regions have different strains in those raw materials. You can develop actually processing industry in around the globe and then actually decentralize some of the manufacturing capacity. Right now, China controls almost 85 to 90% of the processing required for all the critical minerals for battery industry, and that's something which India as well as Europe and US is trying to break that monopoly, so that we can have a more diversity in the supply chain and we do not get affected in case of another pandemic like what happened with COVID. In terms of this global race, as I mentioned, China currently has more than 70% of the global manufacturing capacity and more than 90% of some of the component processing capability. But this is likely to change in the coming decade, as you can see from these maps showing all the facilities coming up in Europe and North America, apart from earlier what I talked about in India. Now, in terms of the innovation, in fact, world is already quite more democratic. US, Europe, even Singapore, Australia, we are seeing a lot of interesting technologies coming up. There are a lot of people who are contributing on shaping up this future around the globe. So each year, through Emerging Technology News magazine, we come up with a World Energy Storage Day issue where we try to recognize our top 50 leaders. So you can see the recent issue on the ETN website. And if you have any suggestions on any additional people who we may have missed out, please do nominate them so that we can consider them for acknowledging their contribution in next year. As a ISA, we are also trying to build a robust ecosystem for startups. Already more than 30 startups have been part of ISA ecosystem, and many of those, such as Aether, Sun Mobility, Ampere, Cell Propulsion, have already received a lot of visibility. But we are pretty sure that we'll have another 5 to 10 unicorns coming out of this startup ecosystem, and we are doubling down and actually next year launching a dedicated accelerator program for supporting this ecosystem. We are also honored that UNIDO has selected ISA and Customized Energy Solutions for supporting UNIDO Facility for Low Carbon Technology Development Innovation Challenge for Energy Storage, where there is $1.5 million funding available for beta deployment of next generation technologies. So again, if you are an innovator or if you are an existing company who is working on an innovative product related to energy storage and e-mobility, please visit lowcarboninnovation.org and please look out for our next round of funding, which should be announced within next month or two. Similarly, there are other incubators like iCreate in Gujarat, where they have launched also Evangelize 21 competition, which is being supported by ISA. So we are not trying to do everything ourselves, but trying to actually bring together all the partners and the ecosystem so that together we can go much further as a relay race and not see it as a race between technologies or different organizations. Particularly in terms of women in energy, I think this is something which again I acknowledge IEEE for the work which IEEE is doing, and I would encourage all of you to get more active. 2 years back, IESA also has launched IESA Women in Energy, IESA V as an initiative, and each year we have been trying to create forums by acknowledging existing women leader around the globe and also trying to figure out what we can do to increase participation of women in the complete workforce around this emerging ecosystem. Part of that will be training, and there already for last 5 years ISA Academy has conducted many on-ground training program as well as online training programs with many partners, including Society of Automotive Engineers, Administrative Staff College of India, IMA, UL, CMET, ARA Academy, and many others. And we have also now launched many of these training programs as a online learning platform through ISA Academy. So you can visit indiaesa.info and look for information. And if you find any course or if you're looking for some training which is not there, please do give us a suggestion. Last thing I would like to just highlight is that there is already a very big global community which has been celebrating World Energy Storage Day on 22nd September each year for last 5 years. 22nd September was picked as a World Energy Storage Day because it is an equinox, so day and night is balanced. So to acknowledge the role of energy storage in balancing grid as well as emissions from transportation sector, this day was picked. And on 22nd September, there is a 24-hour marathon event which gets organized. We have already done 2 events in last 2 years, where first year we had around 75 speakers from 20 countries covering insights, and this year we had more than 175 speakers from 35 countries, and the event was attended by participants from more than 118 countries. If you want to know more about such activities, you can visit ISA website, as well as we have a dedicated news site, Emerging Technology News or etn.news. There is also podcast available as Emerging Technology Radio Podcast, and many knowledge papers and white papers are also available on ISA website. So with that, I would like to conclude saying that there has been tremendous improvement which has happened both on technologies as well as on policy frameworks. The energy storage sector has shown tremendous learning curve for cost reduction, but it is not going to happen everything just by waiting for technology cost reduction. You are going to actually have to deploy the projects, learn from its experience so that you can optimize these projects and get additional benefits. So there is tremendous collaboration opportunity. We should learn from each region. And again, as I mentioned earlier, this is a relay race. Let's win together the race against the climate change. So with that, I would like to once again thank Preeti and organizers for giving me this opportunity and sharing these insights. If there are any questions, time permitting, I'll be happy to answer. Thank you.
Thank you so much, Rahul, for that wonderful session. It looked like the breathless music from Shankar Mahadevan. It was like in one go, everything covered all together. That was really wonderful. Uh, in the interest of time, we may have time for just one question. So recently, we have seen quite a lot of auctions being carried out in India, and every time the tariff rate is getting reduced, and this is in fact affecting the project developments, both wind as well as solar. So, do you see any kind of challenges in applying this energy storage to these systems with this kind of a fall in the development of renewable projects?
No, so again, it's a dual-edged sword, right? So one is, in fact, the fall in prices is great because that's where it is becoming more affordable, and people are now looking at how do we utilize more cheap energy which is coming from renewables. But obviously, you have to match the timing. So that's where I think storage is playing a role. And in terms of, I think the tendency sometimes which people have where, oh, should we wait for another 2 years? My answer is like, you don't do it for anything else, right? For cell phones, 2 years down the line you are going to get a better cell phone, but you are not going to go back to landline or a pager waiting for that cell phone to save some money. So the key part is, can you identify applications where you can say that, okay, if I go with the current price, I'm going to find more productive use, I'm going to save as compared to my alternative cost, and then you don't need to worry about it. And again, right now we are looking at like less than 1% of energy getting stored, right? So we have a very long way go where storage really becomes a mainstream contributor. And similar to solar, where yes, people may complain and say, oh, solar used to cost 17 rupees, but if you see right now we have 100 gigawatt renewables deployed, and out of that maybe first 100 megawatt solar got paid 17 rupees. If you calculate the levelized cost of 100 megawatt at 17 rupees versus now most recent 10 gigawatt at 2 rupees, that's just a few paise on top of it as a total cost. So that's the approach which needs to be taken. If you keep on waiting for just next cheap prices, those will never happen. And especially as a India, if we want to create a manufacturing ecosystem, manufacturing economy, then we need to start creating opportunities so that manufacturers can invest in next generation technologies and start developing that. And once those technologies scale up, then everyone will benefit from the cost reduction, further cost reduction. But we should not be wasting time in just waiting for manufacturing costs, because the biggest thing is, even 5 years before earlier, when prices were at $500 per kilowatt hour, there were many opportunities where we could have saved money against the diesel generators what we have been using, and we could have actually had that entire storage paid off by now, even by installing it at $500 per kilowatt hour. By not installing storage and waiting for storage prices to fall down, we have not saved money. We have just paid that money for dirty diesel and created more pollution in the interim. So that's what people need to realize, that there is alternate cost which you are already paying. So as long as you can develop these projects within that framework, you should go ahead. And particularly if you can start valuing some of the environmental parameters, then I think it's a complete no-brainer. Then I think people should not be even asking these questions.
Thank you so much, Rahul, for that wonderful answer and also the presentation. I really appreciate your time and the effort that you have taken to be with us and share your valuable experience on energy storage and what can be done by our young professionals on working in the energy storage sector. So, as a token of gratitude from IEEE Power and Energy Society Young Professionals team, hosting the Powering the Future Summit 2021. Thank you so much, Rahul, once again for joining us and sharing your valuable insights.
So
Looking
it's a
forward to
pleasure.
working with you.
I'm a member of IEEE since 1997. So again, happy to contribute, and thank you for all the volunteers like you who make these type of events possible for all the rest of the members. So thank you to all of you.
Thank you so much, Rahul. Looking
Sure.
forward to collaborating with you in future events as well.
Yes.
Vehicle to grid concept is one of the smart grid technologies which involves the EV to improve the power system operation. V2G concept allows the energy exchange between EV and the power grid, which can provide numerous services to the power grid. To hear more on electric vehicles and its impact on grid integration, I would like to invite Rekha Sharma, founder of Solforex Inc. Rekha has over 15 years of experience in energy markets, grid reliability, transmission and distribution, power plant design across companies like California ISO, Liberty Utilities, ABB, and Siemens AG. She is the founder of Solforex Inc. and leads innovation and strategy. As energy SME, she is actively involved in designing the in house software products. In previous roles, she has managed development of energy market and grid reliability, along with integrating energy storage, renewables, including solar and wind, to the Western American grid. She has developed applications like meshed short circuit, World War optimization in network management suite, including the energy management, distribution management, outage management, and SCADA. As part of Siemens engineering team, she designed multiple gas coal power plants and led the engineering efforts of nuclear facilities. She has masters in electrical engineering from Texas A&M University and bachelor's in electrical engineering from Delhi College of Engineering and MBA from Rotman School of Management. Welcome, Rekha. You may now take over the mic.
Thank you, Preeti. Can you see my screen?
We can see the screen, Rekha.
All right. So I'll start. Hello, everyone, and thank you, Preeti, for the invitation. I will be talking about the impacts of electric vehicles on power grid. I'll just start with the conventional electricity and take you through the journey how renewables were introduced mainly around last decade or two, how they impacted and how EV just adds a dimension to it. So as a person who has sat on the control room to balance the grid for almost a decade, I saw a graph how I think simple our grid was a decade ago and how complicated it is becoming. Still, with the tools and the technology, we're able to balance it. Of course, everyone has electricity, at least in North America. I can say that at any point of time, we make sure that we have electricity at the cheapest rate, and over the years, we have made it even cheaper for the consumer and reduce the emissions over the years. So just taking down the lane of history, how our conventional electric grid used to look. We used to have generators and then the transmission line distribution, and then it used to reach home. But that's passe. Everywhere we talk about microgrids, we talk about DERs, distributed energy resources. Why we moved from this conventional grid was definitely there were high losses. It was expensive transmission system, and with the solar rooftop and with the DERs, we are able to manage the power at the load in a better way. Still, just to tell you like how our grid used to look in like 8 years before, we were predominantly coal. Around 40% of the energy used to come from coal, 27 from natural gas. Renewables was still early, just 4-5%, like 8 years back. It was there, but it was still early. And we had nuclear around 20%. One big advantage of this grid is the carbon emission, and that's where the whole effort of making the grid renewable, having a lot of solar and wind plants, it started. It is initiated by government policies. We have set targets. Let's say I can talk about California, that by 2020 we should have 50% solar, 50% renewable, sorry. And then once those such policies come, then the whole engineering and, like the technology, our kind of people, we make that happen. And let's take this journey together, how it impacted us. So just to tell you how a load profile looks in a day, very intuitively, the load is very less in the nighttime. And then in the morning, it rises. We've seen that it flattens out during the day, and then again, there is a peak in the evening, and then again, it dies down towards the night. What I've seen over the year is it just to flatten and in the afternoon, but then over the time, with the more solar rooftop being installed and more microgrids and everything installed, this instead of being flat, it is actually curving down. And I think I have some displays to show this. This I will probably run through fast. I just want to show that how much planning and how many organizations are there to make this happen. We have FERC in America, that's Federal Agency for Regulatory Commission. We have NERC, North American Electric Reliability Corporation. We have ISOs, which are independent system operators, and we have energy commissions. And I am assuming everywhere in any part of the world, we have so many agencies making sure that the grid is reliable, it is doing what it's supposed to. Still, it has energy commissions to look into the future and making the policy which are right for the human race, like the carbon emission goals, etc. Now let's just focus on the first problem, the first big jump in the technology that we had was influx of renewables. That's, for me, it's the case one, where I have a renewable generation on the supply side. My whole grid, the conventional grid that I talked about, the dynamic change in one decade, one on the renewable, which was supply side, because I have supply, which I don't control now. Coal and natural gas, we used to generate whenever we want, but now solar and wind, we don't control that. Now with the EV, not the problem, but the change is on the demand side, that I can, like, for me, it's just a load that I can charge and discharge. So they're just in two sides of the grid for me, supply and the demand. A little bit on the energy policy initiatives that we have seen in last one decade was, as we see in this graph, you can see how US electricity generation is, first of all, the load is increasing, and we kept increasing our coal and the natural gas production till around 2000, 2005. But then after that, the coal is actually decreasing. We're still holding on to natural gas for the same problems that Rahul spoke about, because of the reliability purposes. But over the years, with the storage and maybe with V2G, we hope we get rid of this as well. The situation or the graph pretty much looks same across the US, across California, across the world. Over the years, renewable generation is increasing, coal is reducing. There are some countries like Canada, they have changed their nuclear reactor. They call it CANDU reactor, that they take care of the base load with the nuclear. But the countries like US, they're getting rid of the nuclear plants also. So slight different in the policies and the timeline, but but the air is all towards renewable. Like over 10, 20 years, we'll see most of the grids will be 100% renewable, or the maximum they can go. I think I will be emphasizing on this, like similar to what Rahul did, that we have solar, we have wind, we have enough penetration of these renewables. But the problem that I said on the supply side, the variability that renewable brings on the table is that we cannot control it. Sun is out when it's out, wind blows when it blows. We are just capturing that energy whenever it's given to us. So over the years, we have noticed that wind blows mainly in the night, and sun definitely is in the day, and there are some valleys. And these valleys are in the morning and in the evening. And if I remind you with this load curve, these are our peaks. So this is definitely not good for the person like me sitting in control room, try to balance the grid, especially when my solar has not come up, wind has gone down. What do? I have to have some natural gas plants to take care of my base load at that time. It takes away the variability that I don't have to cut the power. I have something that I can plug it in. This curve is the load curve, which tells exactly that I said that initially we had the morning bump, the evening bump. Now, over the years, this is from California. It's called duck curve. We have similar curves in Australia. They have called some geese or goose curve. But this is the pattern that is coming with renewable, especially with the solar rooftop, that the net load is reducing in the afternoon time. Intuitively, if you think that any household which has a solar rooftop, it doesn't take the power from the grid in the peak time. In summertime, they usually generate enough from their solar rooftop. They don't take it from the grid. Instead, they sometimes give it to the grid. So what happens in nutshell, that the net load actually reduces. But one problem, especially for for grid operator, it is doing is when sun goes down, there's a big ramp. There was already a ramp in the evening, but now with the solar rooftop, it's just amplifying. And this increased ramp right now, like till the beginning of this year, it was around like 5,000 megawatt or 6,000 megawatt. If you see here, it's 12,000 and it's going at the peak of 26,000. So this is like one of the worst, like how in 1 hour I'm going to have 10,000 megawatt generation and this has to be controlled. So it'll come from natural gas, it'll come from peakers, the hydro generation. So but still over the years it is just becoming more and more. You can see the plot was around 2012, this plot was like high up, and every year it's just going down. So energy storage is what we that was our solution last year. We pretty much on 2020 is when camel's back just broke, or the duck's curve just broke, where this ramp became too much, that having a peaker, having a fast start generators, they were not enough. So from last 1 year, we have installed around 2,000 megawatt of battery storage in California just to handle this problem. Now let's come to the other problem that I was talking about, the newness of EVs. EV for us is just a load which gets charged at any point of time, at any place. So it has two factors of variability. One is the place, and one is the time. So you can charge your car anytime. You can charge it at home, or you can charge it in the in the mall that you went in. You're going for a trip, you stop it in between for the lunch or something, and you charge. But what it means to us as electrical engineer or power system grid operators is I forecast my load so that I can generate enough electricity to meet that charging power that you would need. these are just basic stats how fast and EV adoption is. And I'll just take you to this graph. This is the graph for concentration of EV by state in US. So you can see in California, Seattle, a little bit on the eastern side, the adoption rate is really high. But if you see the numbers, it's still 3 to 5 people per thousand in the population. So if government has a policy to have all the EV cars by 2050, like they're going to retire everyone, how much the number will increase? Right now, it's like maximum that I have is 5 or 10 in thousand, right? So how much the load will increase? Just to give you an estimation on how much load one car, like if you have a Tesla in the house and you're charging in the house, if your load was X before, and if you're charging a car in the house, it's 50% more. So just that car is X by 2. And if you have 2 cars, you just increase the load by 100%. I think I skipped one good slide. Is definitely we have to go through. There are the challenges that we are facing because of this EV adoption, but it doesn't mean that we shy away from that. We will find solutions, but because efficiency-wise, the EV cars are 60%. They are able to take the 60% of the power which is from the grid to the car, while the conventional gasoline vehicles only takes around 20. At best, no emission, no pollution, it's green, and operating cost of an electric car is actually less than a gasoline vehicle. So economically, environmentally, that's the right step. We have some challenges, and we as electrical engineers, power system engineers, together we are facing it, and we'll solve it over the years. One small thing I want to say is the level of charging. Like not all charging are same in terms of load. We have level 1 chargers, level 2 chargers, level 3 chargers. Level 1 is just you take the plug and put it in the house, but that's very slow. Nobody probably does that. It'll take the whole day for you to charge the car. Of course, there will not be any time to drive it. The fastest charging is called DC charging, where you can just take the car to like a mall where you have those charging stations. You can charge a car in 20-30 minutes. That's called DC charging, and that takes the maximum amount of load from the grid. I just put in some connected designs just to show that, of course, every car is electric car, but then the connectors across the world, across US, Europe, Japan, China, they're all different. It's just the socket, like how their grounding is done, how their line 1 and neutrals are designed. They are different as of now, but what I've seen in last 1 or 2 years, it's kind of merging. There are some universal connectors coming in the market. So if you have a car here, and if I go back to India and I want to take my car along, probably I'll be able to take, because there'll be a connector. This slide has this small formula I just put in there just to put it out there, like what it takes. Like when somebody says the charging time is going to be just 20 minutes versus like 10 hours that you take in the house, it is coming at a cost. Your battery capacity. So charging time is battery capacity divided by the charging power. So battery capacity for your car is same. If you take 10 hours to charge a car versus if you take 30 minutes to charge a car, what you're changing is charging power. So that is that was the second dimension that I was talking about, where we're gonna have surges of the load demand if a lot of people started fast charging at various places. This is just a charger terminology I put in out there. Like you see a lot of charging stations across. So just as engineer, we should understand there is charging station. Here, this whole thing is station. All these pillars that you see, we call them EVSE port, and all the the things which goes in your car, they're called connector, and that's the terminology that we stick as industry. probably I will not go too much in this, but this is just to show how our conventional single line diagram changes with the EV in place. We have a full circuit within the car itself. When you plug it in, it's just not that everything goes in the car. If you look at the PEV, you have AC/DC converter there, and then you have again, the DC to DC converter, you have a battery pack, you have full BMS, the battery management system, because no matter how much electricity you're putting in the car, there is a battery management system, because to protect the performance of the battery, the quality of those cells, they have full computer system embedded in the car, and that's how complicated these cars are. It does add weight to a car. Like any EV is heavy right now because of these battery pack, but it's quite fascinating, how much they're able to do it within the car. Like the whole electric system is embedded in the car right now. So this is just to demonstrate one more time what are the charging patterns that we have seen over the years. That we see that L2 charging is around 70% in the, across the US. Fast start right now is still 7%. And we have started seeing the problems already, those surges. So we, as an industry, we have to project how much percentage of this fast charging would be 10 years, 20 years down the line, and then probably create some solutions around it. Now let's come to the problems and the challenges that we see, and that's what Solve for X is all about. We see these challenges and we try to eradicate them. So we're working on 2-3 main things. One is the charging behavior. All the car and the charging people, the charging manufacturer, they always say that you come and charge at any time. If you do that, you're just making, as I said, variable loads for me. One more problem which it has is all the EVs are focused in big cities right now. In California, it's LA and San Francisco. Those networks, those electric networks are already very congested. Now, if you add in a mall 10 chargers and cars starts coming and charging at any every time, that just adds the load. And if you have 10 cars charging at the same time, how much electricity requirement increases at that node is immense. How am I going to create, generate that much power, and also without burning my transformer, without burning my electric wire, I'm going to deliver it to that station? That's the challenge that many of the utilities might be facing. Of course, there are a lot of solutions that we have out there. Utilities have this time of day rate. We are educating our customers to say that please don't charge in the daytime and the peak time, especially those times that are challenging for us to manage the grid. We give them incentives to charge in the nighttime. There is a lot of battery, the standby battery coming in the grid now. Demand response. I think 2 years back, I know there's a company which just enrolls people to not use electricity in the dire state and give them some cash back, some incentives, and that's very successful. So anything that we as industry can do to flatten the demand, that will be the best solution. Of course, it will not get totally flattened, but then whatever peaks we can remove, that should be our focus. Now in future, so all that we are doing already. Now in future, a lot of companies right now, they're pushing towards virtual power plant. Behind the meter is a thing now. I think 2 years back, not many people in America had behind the meter storage solution. Last year was a game changer for that. We have dynamic pricing schemes. We have one thing that the electric vehicle people are doing is they are introducing long range battery, and how it helps us as electrical engineers is if you have longer range, definitely you'll not do the fast charging, and you'll do it at least less number of times in your long trips or in your day-to-day life. I think I'll end with a note that definitely that's a positive thing that we're doing to environment, and we should do it. Whatever challenge comes in the way, we'll face it. For now, it's very new to us. That's why we are not just used to these problems, but there are a lot of people working in the industry, and we see very good solutions coming along.
Thank you so much, Rekha, for that wonderful presentation on the electric vehicles and covering all the challenges with respect to connecting to the power grid. In the interest of time, maybe we have room for one question. Do you think, as a common man, in order to avail this electric vehicle facility, is there any kind of special education or awareness that is needed? Because we are dealing with power grid, and not everybody knows what happens when you connect this electric vehicle to the grid. So, is there any particular awareness or education that is needed for a common man?
Definitely. Means first thing is, like I said about the peaks, we are doing our best. Like, at least in California, we keep on giving those pamphlets and messages to from utilities to our residents, that when they should not be charging the car. Of course, when you have to charge, you have to charge, but we are giving incentives to people that when they don't have to charge this. In fact, in India this year in August, there was a big drive that we went and spoke to all the students, facilities. I think it was in Andhra Pradesh. It was a government-funded project that we just have to go and put awareness. We just had to create some dashboards so that people can avail. And so Solve4X is all about creating awareness so that we can flatten that demand curve. One thing we can do is avoid fast charging as much as possible, and do it in the night if you could. But if you can't do, then it's
okay. Thank you so much, Rekha. So, I would like to thank Rekha for spending her valuable time with us and talking about her experience and knowledge on electric vehicle and its impact on grid integration. On behalf of IEEE Power and Energy Society Young Professionals, we thank you from the bottom of our heart. Thank you so much, Rekha, for spending your time with us.
Thank you. My pleasure.
Another trending topic in the renewable industry is green hydrogen. To put in simple words, it is hydrogen fuel that is created using renewable energy instead of fossil fuels. It has the potential to provide clean power for manufacturing, transportation, and more, and its only byproduct is water. But what does this physically mean? What impact does it bring to the renewable sector? To get answers for these and to know more on green hydrogen, I welcome Vinay Vyas, Vice President IBD Engineering at Acme Cleantech Solution Private Limited, working on India's first renewable energy integrated green hydrogen and green ammonia project, utilizing his expertise in electrolysis and fuel cells. Prior to that, he was the Director Global Engineering Operations at Canadian Solar to support regional business units. Vinay possesses extensive knowledge about the economic prospect of energy and practical implementation of solar photovoltaic system through two master degrees, Masters of Engineering in PV Solar Energy from UNSW and Masters in Energy Economics from UTS Sydney. He was actively involved in more than 5 gigawatt renewable energy projects development across the globe, and these projects cover various types of renewable energy systems, including green hydrogen, green ammonia, large scale grid tie systems, rooftop solar, standalone battery type, building integrated photovoltaics, and many more. Further, Vinay has a comprehensive understanding of renewable energy market with experience working for different solar PV business models, long-term IPP, short-term solar project developer, and global EPC. His specialties include solar photovoltaic systems, green hydrogen, energy storage, and economical review of projects. It's my pleasure to welcome Vinay Vyas to the summit. Over to you.
Yeah, hello everyone, and thanks for the invite and thanks for the introduction. So I'll just start sharing my slide. So can you see the screen? Or
Yes, it's visible.
is visible? Okay, excellent. So friends, I'll be speaking about energy transition and the role of hydrogen. The agenda will be a quick brief about Acme Clean Tech, and then present energy scenario, applications of hydrogen, national hydrogen mission in India, and what will be the demand of hydrogen in India, strategy for net zero emission, and what are the challenges and opportunities for hydrogen in present scenario. So brief about Acme Group. In 2004, Acme entered telecom business, and they have significantly reduced the operation cost of telecom towers. And in 2010, they entered renewable energy segment. And in 2014, they came up in lithium-ion battery storage business. In 2017, they entered charging and swiping business, battery swiping business, mostly for mobility application. And in 2018, they were the largest renewable energy developer in India. And last year, in 2020, they were the first company in India to establish green hydrogen, green ammonia project. And that seems to be one of the prime use in energy transition in India. Acme has projects across India, around 6 gigawatt of portfolio, and we have end-to-end expertise, including design, engineering, procurement, construction, and managing our projects. We have received a lot of award and recognition for all our innovations and projects. We've been Project Developer of the Year, Best Solar Company, Company of the Year, Business Leadership Award, and various other projects in last many years. So friends, sustainable energy transition is a transition from fossil fuel, carbon fuel to renewable green energy. And there's a famous saying is that Stone Age didn't end because of lack of stone. Similarly, oil age will not end only because world is running out of oil. There are many other reasons for it, and we'll see the energy transition and sustainability requirement. So in the present energy sector, the global energy share of coal is drastically reducing, and this is the first time in last 50 years low carbon technology overtook coal as a leading source of electricity in 2019, and this share is further increasing in a global energy sector. If we look about energy transition, share of renewable energy has increased in last decade, and it's going to be significantly increased in coming decade. But if you look at the entire value cycle and the entire other sources of energy, only by renewable energy and electricity we will not be able to achieve net carbon zero or the environmental goals which are set as per Paris Agreement or other agreements which are there. So there is a requirement to decarbonize other sectors, other industries other than electricity to achieve these goals. And to achieve this goal, hydrogen is going to play a vital role, and we'll see in detail in coming slides. So if we talk about specifically energy sector in India, from 2000 to 2019, there's a drastic increase in GDP, and that has increased the overall energy requirement. But still, 70% of energy needs are coming from fossil fuels, with some contribution from renewable energy. And if you look about carbon emission in present scenario, power sector plays a major contributor, basically due to the carbon coal-fired plants. And in industry, iron industry, steel industry plays 35% of the share in carbon emission, and green hydrogen can play a vital role in reducing carbon emission and becoming more green and clean iron industry. And we'll see how it happens in various other industries. Similarly, in transportation industry, we are seeing that heavy vehicles like trucks and other vehicles contribute around 50% of carbon emission. And these heavy vehicles so far are not electrified, they are not battery operated. There are limitation for heavy vehicles or large duration vehicles to be operated through battery, and that can also be overcome through green hydrogen. And green hydrogen can play a vital role over here. Similarly, in building, agriculture, we can have green ammonia to reduce our carbon emission, to produce higher fertilizers and other chemicals. So we'll see all applications of hydrogen in coming slides. Friends, so we know when we talk about green energy, it's more solar and wind energy, and these energies are intermittent in nature. To achieve net zero emission, so nowadays net zero emission is becoming center of policy for most of the countries, and achieving net zero emission through this intermittent renewable energy is very challenging. To overcome intermittent nature, we can use batteries, as Rahul has explained, the various applications of battery and how we can overcome the variation in renewable energy in a day or a year through batteries. But friends, India is not having large lithium-ion reserve, and if we want to overcome these challenges through batteries, we have to import lithium-ion, and that can increase our fiscal deficit. And to become green and clean energy power, and to become Atmanirbhar or self-reliance India, green hydrogen can play an important role. And we'll see how it can contribute in reducing our carbon emission. So what are the main drivers for green hydrogen? So as Rahul also mentioned that, there are other sources of energy. There are thermal power plants, there are gas power plants. So why we are talking about renewable energies, battery and green hydrogen? So one of the prime driver of green hydrogen is global strong push to limit carbon emission, to achieve net zero emission. There's only 10 years left to achieve our environmental targets set in Paris Agreement. More than 60 countries has committed to be net zero emitter by 2050. And to achieve that, we have to decarbonize not only electricity sector, but various sectors which we discussed, including steel industry, fertilizer industry, transportation industry. So that's the main driver for green ammonia at the moment. Second main driver for green hydrogen is falling cost of renewable energy and hydrogen technology. At the same time, the efficiency and the technology is improving. Most of us who are in green hydrogen business are aware that cost of electricity plays a significant role in the operating cost of green hydrogen. And we have seen that cost of renewable energy has drastically gone down in last decade, and in coming decade also it has been predicted that it will further reduce. So that reduce in renewable energy costs will help in achieving more economical green hydrogen. At the same time, electrolyzer which is used to produce green hydrogen, there are many companies who are setting up gigawatt factories, and through scale of economics, to improving the technology, the cost of hydrogen is also going down. So these are the main factors which is governing the green hydrogen business. And there are various indicators which are supporting this requirement that more than 70% of the global GDP is linked now with green initiatives, green energy, green hydrogen. In last 2-3 years, there are more than 60-70 countries joining Green Hydrogen Council. There are funds allocated across globe to initiate green hydrogen business. Their policy being set in various countries to expedite the process of green hydrogen and utilize its advantage in various industries. So friends, as we are talking about, there are various applications of green hydrogen, right from transportation to powering buildings, to powering industries, to industrial feedstock, large transportation, in steel industry, combined cycles, utilizing hydrogen in fertilizer industry. So this slide gives a brief about all the applications which hydrogen can cover and can help in reducing the carbon emission. In this slide, friends, we can see a value cycle of hydrogen. So we require renewable energy to produce green hydrogen through electrolysis process. This process can be centralized or decentralized. In decentralized process where we produce hydrogen through renewable energy, they can be consumption at the same place. We can have fuel station or utilization of hydrogen without any transportation or storage, and they can be fuel station or end consumption at the same location. Whereas we can have centralized production where it need to be further converted into green ammonia or other fuels. It need to be transported to ships, trucks, or pipes. And then there are a number of applications of green hydrogen, including transportation. In transportation, Rekha has nicely explained about the charging station and challenges and how we are overcoming the challenges of transportation through smart charging. But again, friends, there is a huge limitation of batteries for large duration transportation, heavy transportation. There is no not viable technology in batteries to support shipping industry, aviation industry, buses or trucks. So in all these segments, hydrogen has an key advantage. It can make these segments reduce their carbon footprints and to be more economical compared to battery technologies. And in car and other four-wheeler technology also, as we were listening, that there can be challenges for charging, right? And I am also and this opinion that in the evening when everyone comes back from the office in their home, they put their cars for charging. So amount of impact it is going to have on the grid will be huge, and it can disturb the grid operation. So there are some challenges in battery cars and battery vehicles, and especially there are some applications of large where battery applications are not viable. So that can be overcome through hydrogen and hydrogen vehicles. Further, in other industries like steel industries, that can reduce their carbon footprints. As we discussed, that 35% of carbon footprints come from steel industry. So there's enormous scope to reduce their carbon emission through hydrogen. Chemical industry can use hydrogen for their to decarbonize. Refinery are presently using hydrogen, but it is a gray hydrogen, and they can gradually reduce their gray hydrogen uses to green hydrogen and reduce their overall carbon footprint. Similarly, in heating or other applications, wherever we are using natural gas, hydrogen can replace natural gas for all the applications. In power sector, hydrogen plays a important role because whenever we have surplus electricity, the surplus electricity or can be used to produce hydrogen. And when we are having a higher load and less generation, the hydrogen can be used to produce electricity through fuel cell or hydrogen turbines and pump power back to the grid. These electrolyzers can also support for frequency regulation, voltage regulation, and smoothing curves for renewable energy sources. So there are enormous applications of green hydrogen in power sector also. So, friends, looking at various application of green hydrogen, there are various agencies looking at the market which will be there for green hydrogen. The IEC Hydrogen Council working on various research to evaluate its applications and the market it can cover. And it has been estimated by Hydrogen Council that requirement of green hydrogen will go more than 100 million tons by 2030, and combining with renewable energy and green hydrogen by 2030 the overall market will be more than 6 trillion US dollars. So there is a huge opportunity, there is a large market which is there, and we see that it is going to help in reducing carbon emission. And later by 2050 the requirement will go further more folds and will be more than 500 million tons. That is predicted by Hydrogen Council. So that's the forecast which we have of utilization of green hydrogen. India has recently come up with National Green Hydrogen Mission to generate hydrogen from green energy. The mission aim is to reduce petroleum uses, reduce the imports of petrol and diesel, reduce greenhouse gas emission, improve the air quality, and contribute to overall diverse and efficient energy infrastructure. And in my opinion, a national green hydrogen mission has main four pillars: to create demand for green hydrogen, economics of scale, reduce the cost for green hydrogen, and at the same time fund R&D project so that we can improve the overall technology and improve the overall economics of green hydrogen. So friends, hydrogen demand in India, we are seeing two cases. One is baseline and optimistic case. And by 2050, if we have a target of net zero emission, we require green hydrogen more than 30 million tons. And key contributor in this will be steel, as we are discussing that steel has a good contribution in carbon emission, transportation, power, refinery, ammonia, and fertilizers. These factors will get benefit from green hydrogen and reduction cost of green hydrogen and increasing their demand. It has been forecasted that cost of green hydrogen as a base case will go up to $2 per kg by 2030. But looking at the recent improvement in the technology, in optimistic way, we can say that we can achieve $1 per kg target before 2030. And there are further technology advancement and policy support is required to achieve these targets. So friends, looking at levelized cost of hydrogen, present cost of green hydrogen is higher than the gray hydrogen. And gray hydrogen, just to keep all informed, that it's the hydrogen which we are producing from carbon fuels. So green hydrogen cost is presently higher, but looking at the technology advancement, policy support, we are seeing that green hydrogen will be much more competitive to gray hydrogen, which is produced by coal by 2030, and it will be economical option for us to consider. So friends, we have seen in earlier slides various applications of green hydrogen in various industries, right from steel industry to fertilizer to transportation, and it can help us to achieve our environmental goal, decarbonize, and achieve net zero emission targets which various countries are aiming. But at present, there are various challenges. Some of the few challenges are that the cost of hydrogen, green hydrogen, is considerably high. There is no existing infrastructure to support green hydrogen. Financing of green hydrogen project is challenging. At the same time, they are not much off-taker to take green hydrogen, because the cost of green hydrogen is slightly higher compared to other sources of energy. And to overcome all these challenges, at initial stage, policy supports is required, government support is required for demand creation. And for demand creation in policy formation, there can be some obligation to industry to buy green hydrogen for a certain percentage. They can blend it in their existing use of hydrogen, or they can use a certain percentage as an obligation to decarbonize their process. Because the cost of hydrogen is higher than other source, the policy support is required for viability gap funding to reduce the gap between other sources and make it more economically viable. Funding pilot projects is required. Government support is required for more R&D projects, and utilizing existing infrastructure. So green hydrogen can be blended with up to 9 to 10% in the existing pipelines. It can be blended in the existing process of refineries and gas turbines. So how policies and government can support in creating a market for green hydrogen is important. It is required at this time. And at the same time, support is required to create new infrastructure to utilize all the advantage of green hydrogen. So that's the brief about green hydrogen, its challenges, its market, and way forward. If there are any question, I'm happy to address.
Thank you so much, Vinay, for sharing your valuable experiences and insights on green hydrogen. So, the topics that we have seen previously have been revolving around in the renewable industry for a long time. And green hydrogen, I guess it was also there, but then it was kind of silent. And this started getting more attention with the growth of renewables. And especially in the last few months, when we see that the offshore wind has been gaining a lot of attention, and incorporating green hydrogen with offshore is something that the industry is looking forward to. And you mentioned quite a lot of applications of green hydrogen, and especially the different sectors that it can be applied. But for the young professionals, how can they prepare themselves in order to have a career or route their career to this green hydrogen area?
Sure. So, see, green hydrogen, as we see, there are a number of application, right from industry to power sector to fertilizer industry. So, what I see that most of the mainstream engineering can be applied over here. It can be chemical engineering, it can be electrical engineering, mechanical engineering. So, all the streams are well utilized, can be well utilized in the hydrogen value cycle. And because this is something new in India and it's a new industry, a lot of energy is required, a lot of innovation is required to drive this further. So I see a vital role of young professionals coming in, giving their innovations and energy to take this industry forward. And I think any question after this call also, they can approach me, and I'm happy to share the knowledge with them.
Thank you so much, Vinay. Right now, with this renewable sectors, being it solar or wind, since it has been there for a long time, it was quite possible to predict the future of these technologies. But with green hydrogen, can we predict something of that sort, which is similar to solar or wind?
Yeah, of course, because it's predictable. It's economical at the moment. If we convert green hydrogen to green ammonia, it's competitive in the market in present scenario. And I will say it's not the energy of future; it's the present energy. And as we discussed that almost 95% of operating cost of green hydrogen is the cost of electricity. And as we can predict cost of electricity in future, that same can be governed to green hydrogen.
Okay, sure. Thank you so much for that response. Do you think this COVID has impacted the development of green hydrogen in India? Was there any kind of significant impact?
No, I don't see, because we had some targets of installing our first green hydrogen, globally first green hydrogen project, what I'm hearing in India. and we did that in within the time frame was given to us. And now we are planning for a larger project in Oman, which will be much larger than what we have done in India, and we are looking at the same timeline, and we will be able to meet that.
That's actually wonderful to know, because when we see that the impact of COVID on the different sectors, we found that the energy sector was the least impacted when compared to the other domains. And that is something which we can be proud of as a power and energy professional. So thank you so much, Vinay, for sharing your experience and covering almost everything of what is green hydrogen and what are the areas that people can look forward to. And as you said, this is the energy of the present, and we should be making proper utilization of it. So thank you once again from
Thanks for the invite. Thank you.
the team of IEEE Power and Energy's young professionals. We would like to personally thank Vinay for spending your valuable time with us. I know you've been quite a lot of busy these days, but it's really appreciative that you took some time to spend with us and share all these knowledge with our young professionals. Thank you so much. Thank you for being part of this event.
Okay.
So with that, we have come to the end of the current session on Women in Power track. I would like to thank all the participants for joining in. We have our next session on IEEE PES Day in another 15 minutes. Hoping to see you all there. Thank you so much. Hope you had a wonderful learning experience. Thank you once again.